Good morning. According to this new program, the third lecture is about dark energy. Although it says energy, it should say dark energy. Just to remind you of something that you've seen many times before, at least in this lecture, is the present composition of the universe. And in this standard cosmological model of LambdaCDM, lambda stands for dark energy, which is 70%, in this model, 70% of the total mass and energy of the universe. Indications that there is dark matter comes from observing the universe on many scales, everything from our own galaxy, dwarf spheroidal galaxies smaller than our galaxies, clusters of galaxies, large filaments, superclusters, large-scale structure, growth of structure, everything from scales of hundreds, scales of 10 kiloparsecs to scales of the entire universe. The evidence that there is another component that we call dark energy comes only from measuring the expansion history of the universe. It's the only indication of dark energy that we have at present comes from the expansion history of the universe. So the evolution of the expansion rate of the universe as a function of redshift is a key quantity. And it's so important, I'll actually show some equations on the next two slides to give you an idea of how and why it is important. The first step is the description of the evolution of the universe in terms of Einstein's equations, which involve a metric. And this is the metric for a space that is homogeneous and isotropic. If the universe is described by a homogeneous isotropic cosmological model, there is only one dynamical degree of freedom, and that dynamical degree of freedom is the scale factor that describes how the universe expands. And the other constant that's entered into the Robertson-Walker metric describing the homogeneous isotropic space is a constant k, which is either +1, -1, or 0, depending upon whether the geometry of the universe is that of a three-sphere, positively curved, closed space, a three-hyperboloid, which is a constant curvature space that is infinite, or R3, an infinite spatially flat space. So this is the metric that's used to describe the evolution of the universe. Almost all of the information we get about the universe is due to observing radiation, and photons travel on geodesics, where ds squared is equal to 0. So if photons travel on geodesics, there's an equation, a geodesic equation, that's dr over the square root of 1 minus kr squared is dt over a of t. So this describes how the coordinate r changes with time. And we can rewrite this as writing it rather than an integral over time as an integral over the scale factor, writing this as a dot times a. Now we introduce an expansion rate of the universe, which is a function of time, which is a dot over a. And we're defining a redshift where 1 plus z is a0 over a. Then there's an integral equation that describes how r changes, the r coordinate of the photon as it propagates in the universe, how it relates to a or z, and it depends upon the evolution of the expansion rate of the universe as a function of z. So a photon emitted from some coordinate r at a redshift z will be detected by an observer today, and the equation for this coordinate r of z is related, and this is either a sine 1 or a hyperbolic sine, and this comes from taking the inverse of this integral, But the important thing is related to the integral of dz over h of z. And an example of how this enters into cosmological observables comes from considering the luminosity distance as a function of redshift. The luminosity distance is defined in the following way. If we point a telescope to some object, the flux of photons energy flux that we receive is the luminosity of the object, how much energy per time it's putting out, divided by 4 pi dl squared, the luminosity distance. So the luminosity distance is defined analogously to the inverse square law in flat, non-expanding space. So again, if we have a source at some coordinate r that's emitting photons at redshift z with a luminosity L, the flux that's measured is the energy per area per time, and the energy per area per time is the luminosity over 1 plus z squared. One factor of 1 plus z comes from a decrease in the energy of the photons as the universe expands, the redshift of the photons. And one factor of 1 plus z comes from the fact that as the universe expands, time is stretched. This factor of 4 pi a0 squared r squared is the area of a two-sphere surrounding with the observer at the center and the source at r of z. So this determines the luminosity distance that's proportional to 1 plus z times r of z. So r of z enters into the calculation of the luminosity distance. And the calculation of r of z, which depends upon the integral of the expansion rate, enters in many observational quantities. The luminosity distance I've just discussed. I will have use of the angular distance as a function of redshift. The angular distance, again, is defined in sort of the same way as the luminosity distance. If I observe a source of some physical size, then the angular diameter is the physical size divided by the angular diameter distance. The luminosity distance depends upon r of z, which in turn depends upon the evolution of h of z. The angular diameter depends upon r of z, which in turn depends upon the evolution of h of z. And I can look at how a volume containing a certain number of galaxies, a number of clusters of galaxies evolve. That depends on r of z, which again depends upon the evolution of h of z. I can calculate the age of the universe at any particular redshift, and that also depends upon the evolution of h of z. The evolution of the expansion rate as a function of redshift or as a function of time is perhaps the most fundamental quantity in cosmology related to many observables. So the expansion history of the universe comes from the standard cosmology comes from the Friedmann Equation, which is just a way of stating the 0,0 component of the Einstein equation. G00 is 8 pi g times T00. And the equation giving the evolution of the expansion rate as a function of redshift can be written in terms of its present value, the Hubble constant, times terms which are proportional to the curvature, plus a matter term, plus a radiation term, plus any other term that contributes to the stress energy tensor. And in terms of an equation, the expansion rate of the universe as a function of redshift is its present value times a curvature term, which scales as 1 plus z squared, a matter term which scales as 1 plus z cubed, and a radiation term which scales as 1 plus z to the 4th. There are 3 constants, omega k, omega m, and omega r, which correspond to the contribution to the expansion rate due to matter, radiation, and curvature today at z equal to 0. So this constant omega m is the present mass density of the universe divided by the critical density that we introduced in the first lecture. Omega r is the radiation energy, again divided by the critical density, and I've recast the curvature term in terms of an omega k, which depends upon the spatial curvature divided by g, divided by the critical density. Now it looks like there are 3 constants to determine in addition to the expansion rate, the Hubble constant, but in fact there's not that many to determine because at z equal to 0, the present expansion rate is equal to h0. So at z equal to 0, we have to have omega k plus omega matter plus omega radiation equal to 1. So this removes one of the constants in the determination, and the expansion rate as a function of redshift can be expressed in terms of omega matter and omega radiation. The radiation contribution today, or the radiation contribution at any time, is small in our universe, and it's less than 1 for redshifts less than about 10,000 or 1,000. So if we ignore the radiation term and think about the late universe, then the expansion rate as a function of redshift depends upon h0, the present value of the expansion rate, the Hubble constant, and omega matter. So this led Alan Sandage to his famous quote that all of observational cosmology is a search for 2 numbers, h0, and he called it Q0, but it's just omega matter over 2. So according to Alan Sandage, the famous observational astronomer, all of observational cosmology is a search for H0 and omega matter. We will be most interested in the expansion rate, so let's talk about expansion rate as a function of redshift. The first thing we have to do is to determine the present value, the local value of the expansion rate, the Hubble constant. So the expansion rate of the universe was discovered, of course, by a basketball player. Not any basketball player, but a basketball player for the University of Chicago, who played on the last decent athletic team of the University of Chicago, the 1909 National Championship basketball team. And there's Mr. Edwin Hubble. It's interesting to look at his original paper of the discovery of the expansion of the universe, published in 1929. This is the great graph that Hubble is credited for discovering the expansion of the universe. So what he measured is the redshift of galaxies, which he expressed in terms of a Doppler velocity. Now, it turns out that the day in physics class that he was told that the units of velocity are kilometers per second, he had basketball practice. So he missed that lesson. So he was wrong here. So he plotted the velocity, or the redshift, as a function of distance. And there's a couple of interesting things about this graph. First of all, it has no error bars. There's this idea, it used to be an idea among astronomers, that error bars just make the graphs ugly. Don't put error bars. The other thing that's interesting about it is what Hubble did was something that my students in elementary physics classes always do in a lab class. No matter what the data looks like, they draw a straight line through it. So if you were, never mind a professional astronomer, but a professional scientist, but a graduate student or an undergraduate, and you took this data in a lab, didn't put error bars on it and drew a straight line through it, I suspect you wouldn't get a very good grade on your lab report. So there's not exactly compelling evidence looking at this graph for a linear relationship between velocity and redshift, between velocity and distance, but nevertheless Hubble was right. This is a modern diagram of the velocity as a function of distance, the same type of diagram that Hubble did in 1929. This is 2005 or something like that. And you see it is fairly, first of all, there are error bars. You can't see them for these down here because the errors are so small, but there are error bars. And I don't have to do a fancy statistical analysis to convince you that it's well fit by a linear relationship. Hubble's original data is not plotted here because Hubble's original data would be down there. So it's not exactly convincing from Hubble's original data, but nevertheless, he was correct. He didn't have to wait for a 5 sigma result to claim a discovery. Okay, so in 1929, Hubble discovered the nearby velocity, the Hubble constant. And another way of doing this is instead of velocity as a function of distance, what astronomers do is plot the apparent brightness of some standard candle as the luminosity distance, related to the luminosity distance, as a function of the redshift of the spectral lines. So for nearly 70 years, astronomers looked in the nearby universe and determined the present velocity of expansion, the Hubble constant. They couldn't look very far out in the distant universe because they didn't have a standard candle, but it was realized in 1998 that you can use supernovae as standard candles and look out in the very distant universe where the apparent brightness is very small and measure the velocity there. So if you compare the velocity in the past universe, in the distant universe, to the velocity today, you can look at the difference in the velocity and determine the acceleration or the deceleration of the universe. This is a not very recent but convincing compilation of data on supernova redshift. So this is confusing astronomical notation related to the apparent brightness of supernovae. All astronomical notation is confusing. It's not readily transparent to everybody what it means. So it's not simple, easy to transmit notation like pseudo-rapidity or anything like that. So bright things are down here and dim things are up there. And this is plotted as a function of redshift. And this is the data, and what's done is it's compared to 2 cosmological models. The cosmological model shown in yellow is the Einstein-de Sitter model, which is the model universe assuming that the universe is spatially flat, so k is equal to 0 in the Robertson-Walker metric, and it is excuse me, matter-dominated, omega matter is equal to 1. This is the model of maximal theoretical bliss. Some people in the US talk about intelligent design. This would be an intelligently designed universe. But that doesn't seem to be the universe that we're in. It doesn't fit the data. What fits the data is another model that contains an additional term in the stress energy density, a cosmological constant, or lambda. So what we can definitely say about the observation is that supernovae at redshift of about 1, supernovae in the distant universe, are about a half a magnitude dimmer than one would expect in terms of the Einstein de Sitter model. If the supernovae are dimmer, then presumably they're farther away. The expansion has been faster. Something's pushed those supernova farther away. And you can you can construct what the supernovae tell us in terms of two parameters, omega lambda and omega matter. And at 1, 2, 3 sigma or so, this is what the data suggests. It's very far away statistically from the Einstein de Sitter model. And the evidence here is that you can only fit this with an accelerating universe and not with a decelerating universe. So the only way to fit the data is if the expansion velocity of the universe today is larger than it was in the past. So what could cause the universe to expand, to accelerate an expansion rather than decelerate? Well, the only dynamical factor, the only dynamical variable in the standard cosmology is the scale factor, which determines distances. A first derivative of the scale factor is a velocity, which is proportional to the Hubble parameter. The second derivative of the scale factor is proportional to the acceleration. And in Newtonian physics, you would expect the acceleration to be minus g times rho. Minus because gravity is attractive, so acceleration is minus g times rho. But in relativistic cosmology, there's an additional term that does not show up in Newtonian physics. This additional term is related to the pressure. So the pressure is kinetic energy density. In Newtonian physics, the velocity is much smaller than the speed of light. The pressure is much smaller than the rest mass energy. And this term is a relativistic term. So the usual figure that you see in textbooks has the scale factor starting at 0 at the time of the Big Bang, 13.78 billion years ago last Tuesday, and increasing but decelerating with a negative second derivative, because any reasonable person would expect the energy density plus 3 times the pressure to be positive. But observations tell us that, in fact, the universe seems to be accelerating where the second derivative of the scale factor is positive. The supernovae are farther away, which makes them dimmer. And the way to have acceleration within the standard model is the energy density plus 3 times the pressure is negative. How can you get a negative pressure, or rho plus 3p being negative? One way, of course, is by adding a cosmological constant, or what we call today dark energy. Let me tell you a little bit about the history of the cosmological constant. It was first introduced by Einstein in 1917 in the first relativistic cosmological model. Einstein had a prejudice that the universe was stationary, that it was not expanding. He also had the idea that the universe is homogeneous and isotropic and finite in volume. So it was described by a three-sphere in the geometry with a positive curvature which tended to make the universe collapse. In order to prevent the collapse of the universe, he added a term, a cosmological constant, which would oppose the collapse due to the curvature and find a static but unstable, as it turned out, solution. So Einstein proposed this in 1917 in order to prevent the universe from expanding. In 1929, Hubble discovered the expansion of the universe, and by 1934, the data was so overwhelming and convincing that Einstein admitted that he was wrong and called the introduction of the cosmological constant my biggest blunder. He didn't realize that 64 years later, astronomers would find evidence that there is a cosmological constant, and they renamed it dark energy. So the lesson here for the young people in the audience is never admit you're wrong. Einstein said he was wrong. If he hadn't said he was wrong, he could have been famous. But instead, he said, never mind, and he's been forgotten by history. Never admit you're wrong. So how does the cosmological constant of dark energy enter? Well, in 1915, Einstein discovered his field equations, where there's curvature and metric tensor and all that geometry on the left-hand side. And on the right-hand side of the equations was the stress-energy tensor. And of course, Einstein's theory of gravity relates curvature of space to mass and energy. So in 1917, he added an additional term, and he imagined it in our modern way of viewing this equation as being on the left-hand side of the Einstein equations. A property of space, not a property, a property of space, not a property of the stress-energy tensor. So we introduced something proportional to the metric tensor. It's the only thing he could introduce over there that has the symmetries that he wanted. And there was a constant, the cosmological constant. Then in 1934, he said, never mind, I'm going to take this out and go back to the equations I originally had in 1915. From a particle physics perspective, or perspective of a quantum physicist, there's also contributions to the stress-energy tensor that comes from the energy density of the vacuum. And if you have vacuum energy density, the equation of state satisfied by vacuum energy density is that the energy density is minus the pressure, so rho plus 3p is negative. So a particle physicist puts this on the right-hand side of the equation. However, there's no way that we can disentangle a cosmological constant that would be added on the left-hand side of the equation from vacuum energy that would be added on the right-hand side of the equation if we express a vacuum cosmological constant as 8 pi g times the energy density of the vacuum. So a cosmological constant has something fundamental having to do with curvature of space, something that would enter in the gravitational data book cannot be disentangled from the quantum effects that would enter in the particle data book. So what would appear in cosmology and affect the expansion rate is a combination of gravity giving some fundamental cosmological constant and quantum field theory, particle physics, etc., giving an effective stress-energy tensor, and they cannot be disentangled. So if there is a cosmological constant, it should be added. It would be an energy density that does not change as the universe expands, does not change with redshift, so it's proportional to 1 plus z to the 0, and it introduces one more constant here in the equation for the expansion rate as a function of redshift. Now, if you were cynical, you might say, well, let's add something that involves domain walls that do not commute, that has an equation of state that's 1 plus z to the first, and you would have 1 plus z to the 0, 1 plus z to the 1, 1 plus z squared, 1 plus z cubed, 1 plus z to the fourth. you say, I'm not very impressed. What you've discovered is a Taylor series. But it's a little bit better than that because, again, there is this relationship that the present value of the expansion rate is the Hubble constant. So omega lambda plus omega k plus omega matter plus omega radiation is 1. That removes one of these constants. The radiation contribution is small for small redshifts. That removes another constant. Omega k, the curvature term, is reasonably well determined from the CMB to be close to 0. And omega matter is, with less accuracy, reasonably well determined. It's something between 0.2 and 0.3. So, in fact, it's not as simple as just a Taylor series. Now, perhaps adding a constant energy density to the vacuum is not correct. Perhaps it changes in a different way as the universe expands, so a more general addition of vacuum energy would have this scaling as 3 to the 1 plus W, where W is an equation of state parameter, the pressure over the energy density. W is minus 1, so this is 0, for a cosmological constant. So perhaps there's another parameter that should be included. And perhaps this parameter should be a function of redshift. If W is a function of Z of redshift, then this term is replaced by something a little more complicated involving W as a function of Z. So we can ask astronomers to measure W, the function W of Z, but it's difficult, impossible to measure a function. What people do is parameterize the function and determine the parameters that parameterize the function. One simple parameterization of the function is a constant, the value today, plus a function that goes to WA for large Z, and at Z equal to 0 disappears. So this is a simple parameterization that would represent a change in the equation of state parameter for dark energy. So people have made the comment, like Sandage, that today observational cosmology is a search for two numbers, W0 and WA. Now, just as the evidence for dark matter was more than the evidence on rotation curves or cluster dynamics, the evidence that there is a cosmological constant, the case for lambda, is stronger than just looking at supernovae redshift. It's more than just the Hubble diagram. The fact that the expansion rate as a function of redshift is described by a cosmological constant comes from the Hubble diagram, something that we call cosmic subtraction that I'll talk about in the next slide, I think. Then other observations that I'll try to get to talk about, baryon acoustic oscillations, weak lensing, galaxy clusters, age of the universe, structure formation. So there's other observations that suggest that there is a cosmological constant. I'll try to get to them. Let me just mention cosmic subtraction. The total value of omega that is come from the CMB is close to 1. Omega matter is approximately 0.3, and this comes from many methods that we talked about in the first lecture. So let's do the following sophisticated mathematical operation of subtraction. Okay, follow me here. 1 minus 0.3 is 0.7. Let me repeat that in case there are string theorists here. 1 minus 0.3 is 0.7. This is not equal to 0. It tells us that not all of the mass density is in the form of matter. And this 0.7 is sort of exactly what's needed to describe the supernova results and the other results. So there's other evidence that there is a term that the expansion history has some kind of additional term. The simplest explanation is that there is a cosmological constant, one number, and we can think of the cosmological constant as being related to the energy density of nothing. The unbearable lightness of nothing is that completely empty space, every cubic centimeter of space, including the cubic centimeter of space under your nose, has an energy density of 10 to the minus 30 grams per cubic centimeter. This is dark energy, but it's also useless energy. If you talk to people that there's energy in space, they think we can drill, baby drill, for dark energy and solve the energy crisis. Because there's 1 million electron volts of energy in every liter of space. That sounds very promising. But we know, of course, that this cannot be harnessed. We know it cannot be harnessed, but actually the U.S. Patent Office doesn't know this. There is a United States patent for a space vehicle propelled by the pressure of vacuum energy, in this case, the inflationary vacuum. And if you look at this patent, which has been awarded, you see the plans for the space vehicle. It consists of 2 graduate students, and they're running root here on their computers, and it involves M theory and radioactive debris. That's why you have students in here rather than professors. So there's a U.S. patent for extraction of vacuum energy driving space vehicles. So it's important application of cosmology. So it is, so let's explore what's wrong with having a cosmological constant of 10 to the minus 30 grams per cubic centimeter. I think a better name for it, I'm looking for sound. I had some sound to play. Over here. Thank you. So it is, I think a better name for it rather than the cosmological constant is, in fact, I like to refer to it as the cosmo-illogical constant. How can we get 10 to the minus 30 grams per cubic centimeter for the mass density, the energy density of space? How do we understand the unbearable lightness of nothing? So I think for the rest of the lecture, what I would like to do is to talk about 7 aspects of nothingness. So the rest of the lecture, I will talk about nothing. So it's the 7 secrets of nothingness, which is sort of Zen-like. So let's put on our Zen robes, light some incense, and think about nothing. I always ask my students to think about nothing. Some of them are really good. Okay, so let's think about nothing. What can we say about nothing? Nothing, I guess. Nothing is nothing is uncertain. The first thing we say about nothing. Nothing is something. A little Zen chanting, please. I'm going to talk that nothing has energy. Nothing changes. Nothing is hidden. Nothing is mysterious. And finally, nothing matters. Okay, let's first turn to the idea that nothing is uncertain. It's based upon the uncertainty principle of quantum mechanics. We live in a quantum world. When we think about nothing, we have to take into account the uncertainty principle. So in the quantum vacuum, nothing is something because quantum mechanics is uncertain, and it's possible for a particle and antiparticle to come out of the quantum vacuum, existing for a brief moment of time before annihilating and disappearing into the vacuum. This nothing is something also leads to an energy for nothing, that nothing has energy. All fields are harmonic oscillators. Photons couple to the virtual particles through, and this is evidence experimentally determined by the Lamb shift, and gravitons should couple to virtual particles, and this should contribute to the vacuum energy. So it's a simple field theory calculation to calculate the energy density of nothing, that nothing has energy. You would just sum over all elementary particles, plus or minus, depending upon whether it's a boson or a fermion, d3k over the square root of k squared plus m squared, 1/2 h bar omega for every mode. So at high momentum, you would end up with the sum over particles dk over k cubed, which of course is quartically divergent, so you put in a cutoff. If you don't put in a cutoff, then you get an infinite answer, and you know that has to be right because it's field theory. Anything you calculate in field theory is infinite, so if you get an infinite answer, you know you're doing something right. But it's a bad prediction because the observation is 10 to the minus 30 grams per cubic centimeter, and a prediction is infinity. Let's take a closer look at it. You can put in a cutoff of the Planck mass and say, well, perhaps momentum, something happens to space, or the uncertainty principle due to quantum gravity. If you put in a cutoff of the Planck scale, you get a energy density of the vacuum of 10 to the plus 90 grams per cubic centimeter, 120 orders of magnitude wrong. So you say, well, perhaps these pluses and minus all cancel. If for every fermion with a minus sign, there was a boson with a plus sign, the total, you'd get infinite contributions, but they would all cancel to give something zero or close to zero. But we know supersymmetry is broken, and if you put in a cutoff scale of a supersymmetry breaking scale of a TeV or so, you get an answer that's 10 to the 60 orders of magnitude better, but still 60 orders of magnitude away from the prediction. So this energy density that you expect from quantum uncertainty is much larger than what is observed. Nothing has energy is also due a contribution from the vacuum. Nature seems to like symmetry and then break it. The way we understand symmetry breaking is through spontaneous symmetry breaking. For instance, there's a condensate around us of Higgs fields in the vacuum. The condensation of Higgs fields in the vacuum in electroweak theory have an energy density of about 10 to the 24 grams per cubic centimeter. If grand unified theories are around, that is a contribution of 10 to the 74 grams per cubic centimeter. Supersymmetry about 10 to the 30. Chiral symmetry breaking about 10 to the 13. All of these contributions are much larger than what is observed. Finally, nothing changes. The Higgs potential changes with temperature. At high temperature, the difference in the Higgs vacuum energy density, there's a difference in the Higgs vacuum energy than there is today. So nothing changes. The energy density of the vacuum changes as the universe evolves. Nothing changes. Nothing is hidden. My friends who are string theorists tell me that at every point in space there are extra dimensions. That's not true. I don't have any friends who are string theorists. But if I did, they would tell me that at every point in space there are wound up extra dimensions. There must be energy corresponding, holding these little extra dimensions in there. That should contribute the energy of the vacuum. Nothing is hidden. Nothing is mysterious. It's the illogical magnitude. What is it related to? The observed dark energy is much different than all these numbers that you can come up with from particle physics. Why is the energy density of the vacuum today so small? It's a mystery. Finally, nothing matters. If there is an energy density in nothing, then it will be an effective cosmological term that determines the ultimate evolution in the expansion of the universe. Without a dark energy, then the universe eventually will either recollapse or expands forever, ever slowing. If there is dark energy, eventually it will take over the expansion history of the universe, and the universe will be dominated by a cosmological term and ever expand, accelerating. So the cosmo-illogical constant is because it's an illogical magnitude. What is it related to? If you express the energy density of the vacuum, 10 to the minus 30 grams per cubic centimeter, in terms of an energy, it's 10 to the minus 4 electron volts to the fourth power. 10 to the minus 4 electron volts does not sound like a fundamental energy scale. Or in terms of a distance, it's 10 to the minus 3 centimeters to the minus 4. 10 to the minus 3 centimeters does not sound like a fundamental length scale. If you express it in terms of a cosmological constant rather than an energy density, the length scale is 10 to the 29 centimeters, and the energy scale is 10 to the minus 33 electron volts. Where in the hell does that come from? There's also illogical timing. This is known as the cosmic coincidence. The early universe was dominated by matter and radiation, and the contribution of the vacuum was to the total energy density was certainly very close to zero. In the distant future, the contribution to the energy density of vacuum energy will be nearly 100%, and matter and radiation will be nearly zero. Isn't it a wonderful time to be an astronomer and a cosmologist, where today we just happen to live at a time where we can observe both? The timing seems a bit illogical. So the simple explanation of the observations in terms of a cosmo-illogical constant is a bit puzzling. But we have to remember that we do not directly observe vacuum energy. We do not directly observe the acceleration of the universe. We do not directly observe the cosmo-illogical constant. We do not directly observe dark energy. We infer the acceleration, dark energy, etc., by comparing the observations, cosmological observations, with predictions of a model. And all evidence for dark energy, acceleration, etc., comes from measuring the expansion history of the universe. And that's done in terms of a model. So in terms of finding an explanation, we can take sides. We can't hide from the data. LambdaCDM is too good to ignore. And again, it's more than supernovae observations as subtraction and all these other methods of determining the vacuum energy. But what this tells us is not what is the explanation, but it does tell us that the expansion rate as a function of redshift is not given by the Einstein de Sitter result. So we don't know an equation that works, but we know an equation that doesn't work. We know that Einstein's equations, G00 is T00, where the Einstein tensor is calculated in a homogeneous isotropic model, the Friedmann-Lemaitre-Robertson-Walker model, is not equal to 8 pi g T00, where the stress energy tensor is just matter. We know that this doesn't work. So what's How can we fix this equation? Well, we can add something to the right-hand side to make the equation work, or we can add something to the left-hand side to make the equation work. Modifying the right-hand side, we can add a term that's a constant, which is just a cosmological constant. Or we can add a term to the right-hand side that's not a constant, that changes slowly with time, involving some dynamics. And here, cosmologists have learned something from particle physicists. We've learned that every time there's dynamics that we don't understand, you invent a scalar field. And the basis for doing this is that there have been so many fundamental scalar fields that have been discovered. So it seems like a reasonable thing to do. So we can change the right-hand side, we can also change the left-hand side. And changing the left-hand side may tell us that the observations are pointing to the fact that there's some theory of gravity beyond Einstein that we have to take into account. And another possibility is that it's just Einstein's theory of gravity, but this is modified due to, and I'll talk about, well, maybe I won't talk about, I'll just mention the back reaction of inhomogeneities. So first, let's look at the tools we might have for modifying the right-hand side of the Einstein equations. Now, as a theoretical physicist, when I talk to my experimental colleagues and tell them about my tools, they laugh at me. They say, well, what does a theorist know about tools? Theorists don't know anything about tools. But I point out to them that in my life, I've owned 2 cars, a British sports car, and a Fiat. Anybody who's owned either a British sports car or a Fiat know that if you own them, you learn a lot about tools because you have to fix the damn things every weekend. So over 20 or 30 years of working on cars, I've learned that the only tools you need in your toolbox, you only need 2 of them. One is duct tape. Experimental physicists always use duct tape. And the other is WD-40. With these 2 tools, you can fix anything. If something moves and it shouldn't, duct tape. If something doesn't move and it should, you squirt it with WD-40. That fixes anything. Now, there are theoretical tools that are analogous to duct tape and WD-40. The theoretical tool analogous to duct tape is something known as the Anthropic principle, or if you speak the language of strings, the landscape. The theoretical tool analogous to WD-40 is scalar fields, or quintessence. So let me first talk about the anthropic landscape duct tape explanation for the cosmo-illogical constant. I've argued that there are many sources of vacuum energy, all of them giving very large numbers, some positive, some negative. String theory has apparently very large numbers of vacuum states. More than 10 to the 500 is the number that's usually quoted. And if you imagine that we do not live in a universe, but rather our universe is part of a multiverse, then the multiverse could have populated many or all of the vacuum 10 to the 500 vacuum states. Of these 10 to the 500 vacuum states corresponding to 10 to the 500 different realizations of low energy physics, it's possible to find a few of them where these large numbers, positive and negative numbers, just manage to cancel, leaving a very, very small value of the cosmological constant. While this is exponentially uncommon, these exponentially uncommon cancellations are preferred because more common values of the cosmological constant results in an inhospitable universe. So the anthropic principle says that we must take into account that we can only live in a universe where the cosmological constant is more or less the value it has now. So our existence in some Bayesian weighting has to be taken into account when we calculate what the cosmological constant should be. This is a wonderful principle because it can explain a 10 to the 120 sigma result, a result that's off by 10 to the 120 sigma. If you do an experiment that you're off by 10 to the 120 sigma, you might scratch your head and say, maybe I've done something wrong. No, just say it's the anthropic principle. To give you an idea of what this means, the up quark mass contributes to the vacuum energy through a condensate that's proportional to m pi squared, f pi squared. In our universe, if you would change the up quark mass in the 47th decimal place, you would lead to a 100% change in the cosmological constant. That's how sensitive it is. So that's the anthropic landscape duct tape explanation of the cosmo-illogical constant. And I'll have to admit, it's more convincing when it's heard if the speaker has a British accent. I didn't quite pull it off. The anthropic principle can explain the cosmo-illogical constant. Perhaps there is no better idea than the cosmological principle, which points out that people without ideas can still have principles. But principles should not be applied selectively. What would the cosmological principle, the anthropic principle mean for particle physics? Does it explain the weak scale, Planck scale hierarchy? Who would need low energy SUSY? Does it mean particle physicists should give up searching for an ultimate theory, give up searching for an explanation of why masses have the values they do, and you give up any dream of a final theory, and perhaps particle physics is an environmental science? So there are implications to particle physics if the anthropic principle is the explanation for the cosmo-illogical constant. Let me turn to the other way of modifying the right-hand side of the Einstein equations that I call WD-40. This involves quintessence, which is the name of the scalar field responsible for the changing cosmological constant. So there are many possible contributions to the cosmological constant. Why is the total so small? Perhaps some dynamics that we don't understand sets the value, the ultimate value of the cosmological constant to 0, but we're not quite there yet. And you can express this in terms of the vacuum of a potential for some scalar field known as quintessence that's evolving, and the fact that it hasn't reached the true ground state yet says that there is a vacuum energy. In order to make this work, it seems that you have to have a scalar field that's very light with a mass of 10 to the minus 33 electron volts. Very light. Can nature admit ultralight scalar fields? Light scalar fields seem to be a problem theoretically, but here you need a scalar field of mass 10 to the minus 33 electron volts. If there is a light scalar field of this mass, does it contribute effective long-range forces? So this is not without problems. Let's look at modifying the left-hand side of the Einstein equation by changing something to do with gravity. And many of these approaches have involved the fact that in string theory, supergravity, etc., there are extra spatial dimensions. If there are branes and universal extra dimensions and some types of theories with extra dimensions, the Friedmann equation is modified, and in fact, the Friedmann equation does not come from the 0, component of the Einstein equations. And the gravitational force law is modified at large distances in many theories with extra dimensions. Let me just talk about one. This is the idea of tired gravitons. A long time ago, an explanation of the redshift was not cosmological, but some crazy person, I won't mention his name, but it was Fritz Zwicky, came up with the idea of tired light. That light is emitted from galaxies far away. It has to propagate all the way across the universe. It gets tired, it loses energy as it propagates. So perhaps gravitons become tired, and gravitons are unstable, leak into the bulk when there are extra dimensions, and that's the explanation. Another explanation is that Einstein and Hilbert got it wrong in 1915. They said that the action was the square root of g times r. Perhaps it's the square root of g times mu to the 4th over r. In this case, Minkowski space is not a solution to the Einstein equations, but de Sitter space would be. And finally, some of us have talked about the idea of back reactions of dark energy. Now, time is almost up, so let me skip ahead and wind down. And, right. For dark energy, there are all these theoretical ideas. You might say nothing more can be done by the theorist. In the matter of dark energy, it is only the observers who can, astronomers who can perform a simply invaluable service to theoretical physics. And this was the quote of Einstein when he wrote to Arnold Sommerfeld, convincing him to mount an expedition to measure the deflection of light by the sun. This expedition had a rather unpleasant ending because it was done in the Crimea at the start of the First World War. So maybe astronomers shouldn't listen to theoretical physicists after all. So my time is up. If I can find my mouse, I will. Oops, I saw it. There we go. Advance to the end and wrap up. For dark matter, I said that a WIMP is a simple, elegant, compelling explanation for a complex physical phenomenon, and the cosmological constant is a simple explanation for a complex physical phenomenon. I think it's neither elegant nor compelling. We don't know what the answer will be. So I talked today in these lectures about the particle physics foundation of dark matter and dark energy. I didn't have time to talk about inflation, but we're searching for the particle physics foundation of inflation. And this idea reminds me of, I think it was 1985 or something like that. I went to MIT and gave a colloquium about particle physics and cosmology. The idea of particle physics and cosmology together was very new at the time. And Philip Morrison, who was in the audience, came up to me later. He said, nice colloquium, that kind of things. And he said, the same thing was said in 1939, just letting me know that I didn't have a new idea, by Niels Bohr, who gave a colloquium at Berkeley. And Philip Morrison asked Niels Bohr about advances in cosmology. And Bohr said, until cosmology and particle physics can be brought together in the same context, there is not much hope for real progress in cosmology. I think the same is true today. Today, cosmology depends upon physics beyond the standard model for dark matter, dark energy, and inflation. And until we can have particle physics and cosmology brought together for an explanation of the nature of dark matter, an explanation for dark energy, and a foundation for understanding the physics behind inflation, I don't think there's much hope for real progress in cosmology. Thank you. Any questions? Yes, sir.
You showed the Hubble data at the beginning. How far off was he actually from the value we measured today?
So the question is, how far was Hubble's original determination of the Hubble constant from the value today? Hubble's original determination of the Hubble constant was 500 kilometers per second per megaparsec. The accepted value today is roughly 72 kilometers per second per megaparsec, so it's off by nearly a factor of 10. The reason Hubble was wrong by a factor of 10 is that his calibration scale for distances to galaxies was off. Had to do with different populations of Cepheid variable galaxies, Cepheid variable stars. Determination of distances has been the fundamental problem in cosmology for roughly the past 6,000 years. Determining, you look through a telescope, you see a star, you see a galaxy, how far away is that? It's a process that you do to calibrate the distance scale. So Hubble was using the wrong calibration, or the calibration that was known in 1929. This has been refined over the years, and now the value of the Hubble constant has changed from 500 to 72. It's been the value of the Hubble constant, like the stock market in the over history, has gone up and down, but it seems to now be stable over a few decades at